Hello, I'm Mr. Howard. In this lesson, this is for my pre-calculus students. We're going to look at more on domain, intercepts, notation, and function values. And the first part that we're going to talk about is why we need to restrict the domain in some cases, or situations where we need to identify what values cannot be included in the domain for some of the functions that we're looking at. So a couple of examples. If we had I'm going to just make some basic notes here. We're not talking about example 1 yet. But for example, if we had x plus 2 over x, we cannot have the denominator equal to 0. So we would have to restrict this domain and say that x cannot equal 0. That's one example where we're going to restrict the domain. Another example might be, and your notes talks about this for your assignment, and a value of x that causes the quantity under an even root to be negative. So for example, if we had the square root of x plus 2, we would have to say that the quantity x plus 2 has to be greater than or equal to 0, because we cannot take the square root of a negative number. That's basically what we're saying here. In the real number system, we can't have square root of a negative number, so we would have to restrict that domain. Another example would be if we cause the argument of a logarithm to be negative or 0. So if we had log of x plus 2, for example, we would have to say here that x plus 2 for this must be greater than 0, because if you take the logarithm of 0 or a negative number, you're going to get an error. It's undefined, so we would have to restrict that domain. So we're going to look at some specific examples later, and I think this will make more sense. And then of course in the real world, when you're applying mathematical functions to real world situations, your domain can be restricted by what's reasonable. For example, your notes talk about how the weight of an airplane can't be negative. So if we had a function related to the weight of an airplane, the domain would not include any negative values, and also it wouldn't make a lot of sense to even have a small number that is much less than an airplane could actually weigh in the domain. So the problem situation can also restrict the domain. Okay, so let's start looking at some examples. Example 1, on all of these, they want us to find the domain and the x and y intercepts. Okay, so we're going to apply that. We have y equals 5x plus 2, which is basically just a line, right? So we have coordinate plane here, and we have a positive slope of 5 and a y-intercept of 2. So y-intercept is something like that. Have a slope of 5, so here's what our graph looks like. So the domain here, notice, of course, we're going forever in the positive x direction and forever this way in the negative x direction. So our domain is really all real numbers, so big R, or we could say all real x. Okay, either way. Either this or this is fine as far as the domain. So the x-intercept is going to be when y is equal to 0. The x-intercept right here occurs when the y-coordinate is 0, so we just set it equal to 0. Y equals 5x plus 2. Subtract 2, and we get negative 2 equals 5x. Divide by 5, and we would get x equals negative 2/5. Okay, so our x-intercept is right here at x equals negative 2/5. Our y-intercept occurs when x is 0, so that's like setting x equal to 0. Okay, so 5 times 0 is 0, so y equals 2. And we know that already because the y-intercept appears right here in the slope-intercept form. So y equals 2 is our y-intercept. Okay. You could also write it 0, 2 here, and we could write this negative 2/5, 0 if we were asked for an ordered pair. Well, they didn't actually ask us for that. Okay, let's look at the next one. Y equals 4x over the quantity x minus 3. So our domain, remember, in this case we're going to restrict the domain so that when we have this 4x over x minus 3, this domain is really all x's except when this denominator is equal to 0. So we just come off to the side here and we say x minus 3 cannot, when that equals 0, what x value causes that? Well, we just add 3 and we get x equals 3. So we're going to say here that the domain, we can just say it's all x's except x cannot equal 3. So we could write it this way. Another way to write it, a second way, would be to say that the domain goes from parentheses negative infinity up to 3, not including 3, and then a union symbol. That means union, so we're connecting two domains, two intervals, from 3 to positive infinity. That would be another way to write this. So in other words, it's all x's except 3. That's another way to write that domain there. Okay. Let's look at the next thing, the x-intercepts and y-intercepts. So the x-intercept occurs when y is equal to 0. So we're going to set y equal to 0. So we'd have, since we have a rational expression or a fraction, in other words, on the right side, I'm going to put this as 0 divided by 1. Remember, we're just setting y to 0, and 0 divided by 1 is the same thing as 0, but it puts it in fraction form so we can work with it. So we have 4x over x minus 3, and then we're just going to cross multiply here. Okay, so we get 0 times x minus 3 is just 0, and 4x times 1 is just 4x, so we end up with 4x equals 0. So we divide by 4, we get 0 divided by 4, which is just 0. So x, when x is 0. So the x-intercept occurs when x is 0, right here. Okay. All right, now let's look at the y-intercept. So the y-intercept occurs when x is 0, right? So we want to know y equals, and we'll just substitute a 0 in for x. Okay, and we get y equals 0 divided by negative 3, which is just 0. Okay, so the y-intercept occurs when y is equal to 0. Alright, I'm going to bring up the calculator here so that we can look at this same situation and just check it with our calculator to make sure that we're right. So we have 4x over x minus 3. If we hit the alpha F1, or alpha y equals, I should say, it'll bring up this menu for numerator over denominator, and it makes it a little easier to put this in. So we just put 4x and then hit the down arrow and put in our denominator now, x minus 3. Okay, and if we graph this thing, what we're really looking for is our x and y intercept, right? Well, you can see right here on the graph, we said that that occurs when x is 0 and y is 0. So 0 comma 0 is both of our intercepts, and you can see that is happening on the graph. And then we also said that we are undefined when x is equal to 3. So we can check that with our table. Notice we have x-intercept when y is 0, x is 0. Our y-intercept occurs when x is 0, so here, same spot, 0 comma 0. That's where both our x and y-intercept occur in this case. And if we look in our table, when x is equal to 3, just like we said, this is undefined, and therefore the value of 3 is not in the domain. Okay, so that's just a way we can use our calculator to check it. All right, we'll move on to the next example. All right, for example 3, so we have y equals the square root of x plus 2. So the first thing that we want to do is identify the domain, and we already said before that we cannot take the square root of a negative number in the real number system. So for this one to identify the domain, we're just going to say x plus 2 must be greater than or equal to 0. So what is underneath the square root must be greater than or equal to 0. So we just subtract 2 and we get x is greater than or equal to negative 2. So this means that our domain is all x's greater than or equal to negative 2. And if we were going to use our interval notation that we talked about in the previous lesson, we could also write this domain as, I'm going to put the D for domain here, so we could write it this way, or we could write it this way. The domain is from -2 inclusive to positive infinity. And remember, whenever we use infinity, we always put the parentheses with it. So either way for the domain statement here. Next, we need to identify the x and y intercepts. So the x-intercept occurs when y is 0, so we'll just set y equal to 0. So 0 equals the square root of x plus 2. We need to get rid of this square root, so we're going to square both sides. Square that, and we get 0 squared is still 0. 0 equals x plus 2. Subtract 2, and we get x equals -2. Okay, so our x-intercept occurs when x is equal to -2. We could also write that -2 comma 0, either way. Alright, next we want to find our y-intercept. So our y-intercept occurs when x is 0. So y equals, we just set x equal to 0, 0 plus 2. So y equals the square root of 2. Alright, and if we wanted to write that, we could write it this way, 0 comma square root of 2. Either way. So our x-intercept, -2 comma 0, y-intercept, 0 comma square root of 2, and our domain is everything from -2 to positive infinity. Let's bring up our calculator here, and we'll put this in. Go back to y equals and clear that one out, and second square root of x plus 2. So we graph it, and we notice right here at -2 we can see that that's where our function starts to be defined, and then it continues on forever in the positive x direction. We can go in our table and see those same things, and we go back here to -2 and it's equal to 0. Again, that was our x-intercept right here. And then if we go to -3, -4, -5, -6, we're getting errors because we're undefined. Notice our domain goes from -2 to positive infinity. Okay, and our y-intercept, we can see that that's somewhere between 1 and 2, and so we're not going to mess with that in our calculator here, but it is, we can see approximately the square root of 2 is between 1 and 2 right here. Alright, so let's move on to the next example. Quickly here, I did pull up the table here so we can see when x is 0, we're at 1.4142, and if we go over to our home screen and put in the square root of 2, we can see that that's approximately that value right there. Okay, so I just wanted to show you that you can still check that with your calculator. Alright, let's move on to example 4. Alright, so now we have a logarithm, and we haven't talked about logarithms yet this year. We will later on, but you did talk about them in Algebra 2, but all we're concerned about now is just finding the intercepts and the domain, so we can just have a little quick refresher on that to talk about it. So we already talked about in the beginning of the video that we couldn't take the logarithm of 0 or a negative number. So this right here, whatever we're taking the logarithm of, must be greater than 0. It can't be equal to 0, and it can't be a negative number. And if you recall what quickly here, the parent function of a logarithm, if you think back to Algebra 2, looks something like this, right? That's not the best graph, but it's not defined at 0 or any negative values. Okay, so let's take a look at this. If we want to find out what the domain is, that means, off to the side here, that x minus 7 must be greater than 0. It can't be equal to 0, and it can't be negative. So we add 7, and we get x is greater than 7. So that means that the domain is good for all x values greater than 7. If we use our interval notation from our previous lesson, which is actually what I would prefer that you do, we would write that as 7 is our minimum value, positive infinity is our maximum here, and we're going to do parentheses, parentheses. It's not equal to 7, so we don't put a bracket around this, and then we always put a parentheses with infinity. Okay? Now, if we remember, this graph that I drew over here was just the parent function, so I'm going to erase that so you don't get confused, because this graph is not going to look that way, and we'll look at the graph in just a second. So algebraically, if we solve this and we're for when y is equal to 0 to find our x-intercept, we would have 0 equals log base b of x minus 7. And remember, logarithms they are the inverse of our exponential functions, and we can rewrite a logarithm in exponential form and work with this better. And the rules say that whatever our base is, our base raised to this power is equal to this portion of the logarithm. Okay, the base raised to this value is equal to this value inside the parentheses. So another way to rewrite this in exponential form would be b to the power of 0, so base raised to this value, is equal to this value, x minus 7. And remember, regardless of what the base is here, anything raised to the 0 power is just 1. So that's 1 equals x minus 7. We add 7 and we would get x equals 8. Okay, so our x-intercept is x equals 8. Another way to write it would be 8 comma 0. Okay, now let's look at setting this, our x value, to 0 so that we can find our y-intercept. So that would be y equals log base b of 0 minus 7. Simplify that, y equals log base b of negative 7. Now remember what we talked about before. Can we take the logarithm of a negative number? No. Okay, so that means there is no y-intercept. Okay, and let's look at the graph, and that will make a little more sense. So we clear this out, and we're just going to use log base 10 because that's what our calculator is set to. So the log of parentheses x minus 7. We graph that, and the graph doesn't show it very well here, but it actually continues on down forever, and this value is actually right here at x equals 8 in our case. So, pardon me, at x equals 7 in our case. So we go to our table and we see all of these negative values are undefined, right? Undefined, 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 because we said our domain was everything from 7, just before 7. So 7 is not included, but 7.00001 is, and then 8 is included, 9 is included, 10 is included, 11 is included. So 7 to positive infinity, not inclusive of 7, is in there. So if we change our table set real quick, just to prove this to ourselves. So if we start our table at 7.0001 and we go back in our table, you see that we are defined there. Okay. All right. So let's we also wanted to check that our x-intercept was 8, right? So let's go back into our table and we'll just start it at 0 again. And when x is equal to 8, our value should be 0, and it is, so that checks out. There is no y-intercept because notice the graph drops here. It's got an asymptote right there at 7, at x equals 7. So there is no y-intercept. It will never cross this y-axis over here. All right, let's move on to example 5. All right, so a little bit different situation here. We're no longer looking for the x and y-intercepts in the domain. It's asking us if f of x is equal to x squared minus 3x, what is f of negative 2? So f of negative 2 is going to be equal to 2 squared, negative 2 squared minus 3 times negative 2. So negative 2 quantity squared means negative 2 times negative 2, which is positive 4. And then minus 3 times negative 2, that would be minus negative 6, which becomes plus 6. So that's 10. So f of negative 2 equals 10. F of negative 2 equals positive 10, and we can type that in our calculator quickly here. Let's bring that up. Y equals, put in x squared, whoops, let's clear that out, x squared minus 3x, go in our table and find when x is -2, and we see we have a value of 10. So that all checks out. All right, let's move to example 6. Okay, here we have example 6. If f of x equals the quantity x plus 3 divided by x, name the ordered pair given by f of 4. So we just rewrite this. We have x plus 3 over x, and that is f of x. And we are asked for f of 4. So f of 4 is equal to, we just substitute a 4 in for x. So it would be 4 plus the quantity 4 plus 3 over 4. So that equals just 7 over 4. And we're not going to turn that into a decimal. So 7 over 4 is our answer. And the ordered pair, notice they asked us for the ordered pair. So our x value is 4 right here. So it's 4 comma 7 over 4. Okay, let's check it in our calculator quickly. We can do that. Y equals, we have, I'm going to do our numerator over denominator to make this easier. So it's x plus 3 over x. We want to go in our table when x is equal to 4, and there we have it, 4 7/4, 4 comma 7/4. So that's correct. Let's move on to example 7. Alright, so example 7, where does f of x equal x plus 7 cross the x-axis? So this is just another way of asking us for our x-intercept. And remember, our x-intercept occurs when y is 0, so we just set this thing equal to 0. So 0 equals x plus 7, subtract 7, and we get x equals -7. So our answer there is just -7, or the point -7 comma 0. Pretty simple. Alright, let's move on to example 8. Alright, example 8 says, if f of x equals x, the quantity x minus 3 divided by the quantity x plus 4, where does f of x equal 5? Okay, so this is saying when is the y value equal to 5? So we just set this thing equal to 5. So 5 equals the quantity x minus 3 over the quantity x plus 4. So we have a rational expression over here, in other words a fraction, so we can put this one over 1, so we have one fraction set equal to another, which allows us to cross multiply, which makes it a little faster algebraically. So we have 1 times x minus 3, that's just equal to x minus 3. And then on this side we have 5 times the quantity x plus 4. Don't forget it's 5 times the quantity x plus 4, so we distribute inside here, we get 5x plus 20 equals x minus 3. We want to get our variables on the same side, so I'll subtract an x and we'll get 4x plus 20 equals -3. We'll subtract 20 here, and I'm going to move over here so we don't run out of room, but we're subtracting 20. We get 4x equals -3 minus 20 is -23. Then we just divide by 4, and we get x equals -23 over 4. So that means that when f of x equals 5, let me erase that. So we have the ordered pair would be -23 over 4 comma 5 is what that means right there. Okay, so let's use our calculator for that real quick. So let's go y equals, we already have it set up for numerator denominator here, so that makes it pretty easy. So we have the quantity x minus 3 on as our numerator, and our denominator would be x plus 4. So if we graph this, we have the graph here, and we're asked for when does f of x equal 5. So when is y equal to 5? Well, the easiest way to do that with our calculator is just go to our y2 and put in 5. So in other words, that's y equals 5. It's going to graph a horizontal line for us right there. So we are looking for this intersection, so we can just go second calc here, second trace, go to intersection, 5, and first curve, we can just do enter, and then for our guess, first curve was the Our rational expression, second curve, is this horizontal line. For the guess, get it as close as possible so it's faster for your calculator. And there it is, negative 5.75. And if we check that, negative 23 over 4 is going to be, negative 23 over 4 is going to be equal to negative 5.75, just like we had on our graph. All right, one more example and we'll be done. In the last example here, we have notes on your assignment. Another way to specify discontinuous domain intervals or any other intervals. Suppose the domain of a function is given by negative 4.2 to 2 and 5 to infinity. This is the union of two intervals, which I actually used earlier in the video, and is often given by negative 4.2 to 2 union 5 comma infinity. So this union symbol just unites two domain intervals. So it says on a number line, draw the points given by negative infinity to negative 3 union 0 inclusive to 9. So if we draw a number line here, so we'll do that right here like this. It's not a very straight line, but that'll be okay. We'll mark negative 3 here. We'll mark 0 here because that's part of our domain, and then we'll mark 9 right here. So from negative infinity to negative 3, and we're not inclusive of negative 3, so we're going to draw an open circle here and then go to negative infinity. So that's this part in pink, and then in green we'll do this part. So 0 is included, so I'm going to draw a solid dot there, and then we go out to 9, and it stops at 9, so it's an open circle, not an arrowhead, not a filled in dot, an open circle. Okay, so that's it for this lesson, and I will see you in the next video.